Like base biology, that might have been like the only class you ever struggled with.
No,
It's so much easier.
memorization.
I know.
I hate memory.
Biology.
There was no
Biology
math.
is so much easier.
So,
Except for
Okay.
chi-squared.
you haven't even them. They don't.
Dude, I just remember the keyword homeostasis.
Okay.
That's it.
Yes.
So here's what we're going to start today, and that's going to be rotational motion. And then we'll cover that today. We'll finish up with angular momentum tomorrow. We'll review on Monday, and then the test over momentum will be on Tuesday. Okay? So just keep that in mind. So don't flip out. These are just lecture notes. It's got all the terminology. And on the back is a set of equations that you do not have to memorize. So don't flip out and go, oh, God, you got to memorize these. No, they're on your equation sheet. Don't flip out. So just let me get these in. Stay. There we go. There goes the world.
Alright, we need to add 40.
That was actually really funny.
Because we added $20 for one thing, we need to add 20 for Olivia.
Oh yeah.
Here we go.
Here,
You want to tell
keep
me
that on him. Who? Keep that on. Keep that camera on. I'm not running the camera. Okay. Add 20 more to us because we added Olivia's money.
I can't even.
Don't ever do it.
Change the 20 to a 40.
Think about it for like probably 3 or 4
It should be
I feel
245.
like you should just go until you die, and that's
No.
it'd be more memorable for
Yeah, you can do it just to
Okay, that works. Whatever.
Yeah, just
Yeah, do it. Do it. It's fine.
It's way easier when I have to
yelling about like freshman heart attack or something.
So the only thing is today my clothes are full.
No, fake your own death.
Oh, I like
On a
it.
suicide note that says you hate freshmen, so you just couldn't take it anymore. And then really just moved to like a different country. Did you know it's legal to fake your own death to get away from family members? You're just no longer a U.S. citizen.
How do you just know that?
He's got a lot of family to get away from.
So can you stay in the United States, or do you have to leave the United
I'm
States?
pretty sure you have to leave.
Okay.
So then
Yeah,
it's,
Canada's not a bad option.
No. Australia's pretty good too.
Rather than like wake up with like a spider bigger than your head on your pillow. I don't know.
Actually, the only spiders that are bigger than your head are in the Amazon. The really poisonous ones are in Australia. Venomous.
The random things that you know is just amazing.
Yeah.
Okay. All right, so here's what we've got is rotational motion. So there's a couple of things that are going to be different, yet similar. So first off, you'll see that all the variables that we use are going to be different than any of the variables that we've used so far. But it's a lot of the same idea. So like this wheel is going to remain at rest until I apply a force to it. And then, but once I get it moving, it's going to keep moving until I apply an outside force to it. Okay, that's pretty simple. Now the other thing that happens when you make things spin, I need this string here. So, hold on. There you go. I struggled with this in first block.
Not time 101.
No, I just want to do like this.
Just gotta make the bunny ear and go around the tree and pull it through.
That is absolutely the only way.
So if this thing isn't spinning, and I let go of it, hold it up and let go of it, it just goes doink. But if I get it spinning, and then hold it up, then it will stay up and process around. Okay? Now, if I spin it the other way,
it'll rotate in the other direction.
yeah,
Ooh.
then it'll rotate around in the other direction. Okay? So, this is why.
The earth is on a string.
That's it, Ethan. Okay, that's it, yep. Tied to the sun, there's no gravity.
Class is over.
Also,
Class is over, gravity, it's all a scam.
It was a great semester with you.
Yeah, gotta go.
I'm glad
We're just
to be
gonna
out
watch,
here, by
we're
the
just
way.
gonna watch videos the rest of the year.
Hey, BB created gravity.
Did you say
BB created gravity.
Okay,
what?
but this
Big
is
brother.
why, I'm guessing at some point back when you all might have actually been physically active and you were like, you'd go out and like ride your bicycles.
I never did that.
And did y'all ever like try and ride it like really, really slow?
oh yeah, and it like wobble
Yeah, why is it wobbling?
because you're going slow.
It's trying to fall over because it
Trying
doesn't
to fall
have
over.
enough-
So it's kind of like this. If I've got this wheel like this, okay, and it'll go doink, okay? because it doesn't have what we call angular momentum. But if I get it spinning, then it stays up. Okay? So, which is why when you're riding a bicycle, it's easier to stay upright when you're moving than it is when you're going slow, because the faster you go, the more the angular momentum vector is, which we'll talk about tomorrow. So, here's the problem when you have a bicycle wheel and things that spin. You have to be able to account for 3 different types of motion. One type of motion is if I just take this and I just throw it, okay, with no rotation whatsoever, right? I just take it and go, screw it, right, throw the wheel. Now, if that's the case, I can just use F equals ma. Here's the mass of the wheel. I want to give it a certain amount of acceleration. That's the force that I apply to it, okay? So that's just throwing it without any rotation, okay? Boring, but we can do that. The other thing that can happen is that you can have motion. You can have angular motion, but it doesn't go anywhere, okay? So it just sits here and spins. So we've got to be able to handle that situation. Then you've got to be able to handle a situation where you have both, where you have rotational motion as it's moving and spinning, but it's also the center of mass is also going down the road, okay? So we got to be able to account for all 3 of them. The first one you already know, oh, F equals ma. Boom, okay, that was simple, all right. Where they begin to spin, this is where you run into complications. So the first thing that's different is that basically linear physicists had taken all the good variables of like distance, acceleration, mass, all that good stuff. And so, Felix, what are you doing? Whatever.
Happy to do.
He loves this class.
Don't we all? All right.
No,
I don't.
we don't.
Okay. So the other thing that's different is that we have to introduce different variables, okay? So this is the Greek letter theta,
Hey, pre-calc.
and then you've got omega, and then you've got alpha.
It's got some cheese.
Now, just because somebody's going to think they're clever, probably McGriddle, and they're going to go, that looks like a butt, okay?
I didn't even think that yet.
Yeah.
Yes.
That looked like a cursive fancy W.
Okay, whatever. And so and I say that because if I don't, then you're going to think you're the first person since ancient Greece to think that looks like a butt. And you're going to think you're funny, and you're not, okay? So let's just get this out of the way right now.
Dude, I think it looks like a butt, I'm gonna be honest.
Matt, since ancient Greek, I think you're the first one.
Yeah. First one ever.
That's crazy.
Someone write that down.
And this looks like a fish. Okay? And first block determined that that kind of looks like a cracked egg.
Looks like a
That does
cyborg.
not make any
Looks like a
sense.
pill.
No,
Looks like a
it's
cyborg.
It looks like a theta to me.
Okay. So basically, you have theta butt fish. Okay? That's the easiest way to
Dude, it
do
looks
it.
like a screw.
Huh?
It
I
does.
can see that.
Oh,
Eli.
Oh, there you go.
Nice. Looks like the top of the
But-
griddle.
Standard, but not a Phillips.
Yeah.
Yeah, okay. Okay, so,
The old fingers
Screw
here.
butt fish.
that just is that's a weird combination.
Not a good order.
All right. Okay, now, here's the other thing that we need to introduce, and that's how we're going to measure revolutions. So, if I take this, okay, let's say for example I got the piece of purple tape down here, and I have it go around one time, that's going to be one revolution. But here's the thing, is that every point on this wheel, whether it's really close to the center or if it's on the outside, is all spinning at the same rate. Every point on there is making one revolution. So we've got to be able to say, okay, well, how can we describe every point in terms of motion? So for those of you that have done this, we're going to let one revolution equal 2 pi radians. Okay? Now, that doesn't mean you have to change your calculator to radian mode. Okay? It's not what we're about. Okay? Now, here's the odd thing about radians, is that radians are what's known as a dimensionless number. They're the only dimensionless number that we're ever going to work with, okay? So, if I say I went 5, okay? We went 5 what? 5 light years, 5 meters, 5 centimeters, 5 feet. Where did you, how 5? I don't know. But if you say I traveled 2 pi radians, that's all you have to say, okay? Because the radians are a dimensionless number, okay? So what you'll see is they're like these ghost years. They kind of float in, they kind of float out. So here's going to be the most important thing. You have 1 revolution is 2 pi radians. Now here's the other thing that you're going to see, and that more so than about any other unit that we have done. You have to keep track of what's a variable and what's not a variable in these calculations. So when you say that 1 revolution is 2 pi radians, it doesn't make any difference in terms of the radius. So if I've got this wheel and it goes through 1 revolution, that's going to be, every point on here is going to move through 2 pi radians. Whether I'm right here towards the center, or if I'm further here on the outside. The Earth, as it rotates around the sun, makes 1 complete revolution. That's going to move through 2 pi radians, okay? Our entire Milky Way galaxy is moving in a circle, okay? We're spinning. So our entire Milky Way galaxy is going to move through 2 pi radians. So the radius is not a factor in determining this relationship between revolutions and radians. Radius is not a factor. So right now, you have billions upon billions upon billions of tiny electrons going around the nuclei that make up the atoms that make up your body, okay? And they're all moving through 2 pi radians, okay? Don't flip out and go, oh, I feel them, right? Yeah, cool. No, you don't. So, no, that's something else that you feel. But the electrons are going around, the Earth is going around, everything's going around. But the radius is not a factor, okay? That's going to be important. So when you look at what this is going to measure, so theta is, and this is what's on the lecture notes that I gave you. So theta is equivalent to like how far something is going to go that's going to be measured in meters. So theta is going to be measured in radians, okay? So you got distance measured in meters, say how far did you go? Theta is going to be in radians, how many radians did it move through, okay? Not a big deal. So omega is going to be equivalent to velocity. Velocity is in meters per second. So if omega is equivalent to velocity and velocity is in meters per second, what's omega going to be measured in?
Radians, omega.
Radians.
How about radians per second? Okay? Because just like velocity is in meters per second, omega is going to be in radians per second.
I was looking at that. Never mind.
Is that good?
Yeah.
Okay. Now, word of caution. Okay? Word of caution. What's the only time that you can calculate velocity by taking displacement and dividing it by time? What's the only time you can do that? You have constant velocity. So the same thing is going to be true here. The only time that you can calculate angular velocity by taking displacement and dividing it by time is if something is spinning at a constant rate. If it's speeding up or slowing down, you can't do that. So you can do theta divided by time to get but you can only do this when it's spinning at a constant rate. If it's speeding up, slowing down, you can't do this. So like when you press down on the gas pedal, fundamentally in terms of your tires, what are you trying to increase?
But.
But you're trying to make it bigger, but you're trying to make it spin faster. Okay? When you hit your brake, what are you trying to do?
Smaller.
You're trying to make a smaller butt. What's your cruise control doing?
Constant.
Constant butt. Okay?
Constant butt?
Yeah. That's it.
Impossible, but yes.
I'm just saying. Okay. Now, but if you're speeding up or slowing down, you can't do this. So if you look at like a clock, right? When you have the second hand, the hour hand, the minute hand, all of those are spinning, all of those are moving at a constant rate. So we could find those values using this. But if you're talking about a car tire that's starting from rest and speeding up, you can't do this calculation. So if this is equivalent to velocity, what do you think alpha is going to be equivalent to?
Meters per second squared.
Acceleration, which is meters per second squared, so this is going to be in...
Radians over seconds squared.
Huh?
Radians
Yeah.
over seconds squared.
Beautiful. Okay. Now, just like there's a whole bunch of different ways to calculate angular or linear acceleration, you can use that equation, you can use distance equals 1/2 at squared, any number of things. There's any number of ways that you can calculate that angular acceleration. Now, here's the beauty of this. All the kinematic equations that you know work exactly with these variables. So let's say that you have a position versus time graph that looks like this. So what's the slope of a position time graph give you?
Velocity.
Velocity, because it's meters per second, right? It's cool. So oddly enough, if I look at a theta or radian per unit of time, what's that going to measure?
Velocity.
Yeah, so this is going to give me how fast I'm going. So just like velocity over time gets you acceleration, guess what? If you've got an omega versus time graph that looks something like this, what does that mean? So here's an omega versus time graph. So what's this? Where does this wheel start at? 0. What's it going to do for the first unit of time? It's going to spin faster, right? Then what's it going to do? Spin at a constant speed. So I would take this wheel, right, and I would make it speed up, okay, for a little bit, and then it's going to spin at a constant speed, and then what's going to happen here?
Slow down.
I'm going to slow it down.
That's going to go in the opposite direction.
But then I'm going to make it go in the opposite direction. Ooh, right? Now if I stop it, then what's this? Now what's that going to do?
Go to 0.
It's going to go up to 0. And then if I make it spin the opposite direction, it'll go that way. Okay? So it's the same idea. So what do you think this area would represent on an omega versus time graph? Radians. It's going to be how many revolutions or how many radians it moved through. Just like on a velocity time graph, that would represent how many meters it went. So it's the exact same idea, okay? We're just using different variables. And even the equations are the same. So, and that's what's on those lecture notes that I gave you. So just like you can use distance equals 1/2 at squared plus v naught time, okay? One equation you've used 100 times. You can just come here and go, oh, that's theta equals 1/2 alpha t squared, and this is just fun to say, and then multiplied by but not time, okay? But not, I don't know why this is fun to say, but it is, okay? And then just like you have v squared equals v naught squared plus 2ad, then you get but squared and but not squared plus 2 times theta alpha. So basically where there's any equation where you see a distance, put in theta. Wherever there's an A, you put an alpha. Wherever there's a V, you put omega. It's the exact same equations. Okay. Now, where you run into trouble is when you have to cross over between linear motion and angular motion. So on your sheet and on your lecture notes, you've got these 3 crossover equations. D equals r theta, you have V equals r but, and you have A equals r fish. Okay? Now, what's common to all 3 of those? Yeah, they're all dependent upon radius, right? So these are like the Pirates' 3 favorites equation because they all have an R in it. Okay? R. So all of them have a value of R. So basically, if you want to figure out how far something goes, take the radius, multiply it by how many radians and move through. If you want to figure out how fast it's going, multiply it by how fast it's spinning, figure out the acceleration, multiply that by your angular acceleration. Now, for now, I want you to pretend that you don't know these and they are gone. Okay? We'll get back to them. So here's what I want to do. I want to take this wheel, okay, and I've got like the purple thing down here at the bottom. And I'm going to roll this thing across until the purple mark gets back to the bottom. So what I want to know is how far did the center of that wheel move when I went from there over to this
Wait,
point?
was it
2 pi radius.
No, it was, I started with it at the bottom.
Oh, okay.
Okay, so it was here at the bottom. And then we'll have it roll across like this until it gets back to that point.
2 pi
2
radius.
pi
One
radius.
revolution, 2 pi radius.
No. I want to figure out how far it's going to go. I want to figure how far the center mass wheel went. Now, let's say that the radius of the wheel is 0.25 meters.
It would be
So what could you find? Olivia. I could find the circumference. Oh, brilliant. How do you find the circumference of a wheel?
2 pi r.
But I'm a fan of 2 pi r. Okay? I'm a fan of 2 pi r, and you'll see why in just a second. Okay? So Olivia says circumference of this tire is going to be 2 pi r. Right? True? So, the other way that you can think about it is imagine if you could take a piece of string and start here and wrap it all the way around the wheel and have it come back to this point. And then take that string and stretch it out. And that's how far the center mass of the wheel is going to travel. So in this situation, you get the circumference with the radius of 0.25. So we're going to take 2 pi times 0.25 meters. Right now, I'm going to work this the math way. Okay? I'm going to work this the math way. So the math people will go, oh, that's the same as multiplying that by 1/4, and then that reduces down, and you get pi over 2 meters. Okay? And then math people go, this is the most exact way to write it. Okay, and it is. Okay, God bless them. I've hung out with a bunch of math nerds. Okay, and it is. It's the most accurate, precise way to write it, however you want to say it. But here's the problem. Have you ever seen a meter stick that measures in units of pi?
No.
No. Okay? I cannot grab a meter stick and say, hey, Shively, I need you to measure out pi over 2 meters. It's like, it's going to be weird, okay? Because so, from mathematical standpoint, this is the correct answer. But from an actual being able to measure it standpoint, this is a train wreck. Because you can't measure stuff in units of pi over 2. Okay? It doesn't work. So let's actually get something that we can measure. So somebody take pi and divide it by 2. It's 1 point something.
1.57.
1.57 meters. Now, that's something that I can actually measure out. I can measure out 1.57 meters, okay? I can't measure out pi over 2. So, from a physics perspective, this is why we have to deal with that, because that's what we're going to measure. Now, so this is a cool thing. Got the circumference, here we go. Nice. But then you're going, well, Burkham, let's talk about this equation. Okay, let's talk about this equation. So here's the deal. If I start with this tire here, right, and I roll it across here until it gets back to that point, how many revolutions did that make?
1.
1, right? That made 1 revolution. Now, we just said that 1 revolution is equivalent to how many radians?
2 pi.
2 pi. Now, just 2 pi. 1 revolution is just 2 pi. Okay, R has nothing to do with this. Listen to me. Radius has nothing to do with this conversion. It's not there. Okay? Now, you go, well, let's try out this equation. Okay, let's try out this equation. So I've got a radius of 0.25 meters, and then I'm going to multiply that by theta, but theta is 2 pi. So oddly enough, you get the exact same answer of 1.57 meters. Okay? I still get 1.57 meters. All right? Go with that. Now, what if that tire made 2 revolutions? Then how far would it go?
4 pi radius.
Okay?
started shaking hands, and then you started pushing real hard, so now it's an arm wrestle.
I'm gonna win.
As long as you don't hit that camera.
It's a very low stakes arm wrestle.
Okay. So,
Turns my stakes. I'll bet.
so if I went through 2 revolutions, what's the only thing that's going to change in this calculation?
2 pi.
2 pi, right? So that would become 4 pi, and then oddly enough, I'd move through 3.14 meters. I'd move through pi meters, okay? Now, here's the deal, and this is the beauty of studying physics, because you can see how it relates to mathematical equations. I'm going to take all these and show to you that these are all linear functions in the form of y equals mx. And you're going, no, they're not. You have distance and radius, and you've got Greek letters and all this other stuff. No, they're all linear functions. I'll show you why. So remember these numbers, okay? So I'm going to plot distance over here, and I'm going to plot theta here. So when we went through 2 pi radians, how far did we move?
1.7.
1.5,
Or yeah, 1.57.
1.57 meters, right? Okay, so that was 1.57 meters. So we got this point. If we went through 4 pi radians, that would be 3.14. Okay? And this is going to go through 0, 0.
Is the radius the slope?
Linear.
That's a linear function. So, here's the question. Can I find the slope of the line?
Yes.
Yeah.
Yes, because it's a linear function, right? So I'm going to go, oh, that's change in y over change in x. So I got a change in y. Let's just pick 0, 0 as our point, right? So that's going to be 1.57 meters divided by 2 pi. So I'm going to take 1.57 meters and divide it by 2 pi radians. You get,
Yeah, 0.25.
you get 0.25. Now, this is a situation where I don't want you to go, oh, that's meters, it's meters over radians, okay? Radians are dimensionless numbers. So here's what's important. What does the slope of that line give you?
No, radius.
It gives you the radius, okay? It gives you the radius. So if you go back to this, all 3 of these equations are y equals mx. You could graph all 3 of these functions, and they'd all be linear functions. And you're going, whoa, they're not. That doesn't look anything like I've done in math class where's the straight line slope. Sure it is. And on every one of these, what does the radius represent?
Slope.
They all represent the slope. So all of these are linear functions. This is what you're going to graph on the y-axis. This is what you're going to graph on the x-axis. Now, here's the physical meaning of this, okay? Here's the physical meaning. So I took this wheel, right? Started here, 1 complete revolution, went all the way across the table. Now I'm going to take this 100-gram mass, okay? And I'm going to put the 100 at the bottom, and then I'm going to roll it until that 100 goes back to the bottom. So I wrote the 100 at the bottom, I roll it till it goes back to that bottom. How many radians did it move through?
2 pi.
2 pi. Was it the same number of radians that this wheel moved through?
Yes.
Yes. Why? It still only went 1 revolution. Okay? So, if it's that little mass, or if it's this big tire, or it's the Earth spinning on its axis, if it goes through 1 revolution, is the radius a factor? No. It's still going to move through 2 pi radians. Okay? That's it. Now, here's what's important though. What's going to happen to the distance, the linear distance that this thing is going to travel when it goes through 1 revolution? It's going to be a lot smaller. Why? Radius is a lot smaller. So here's what I want you to see. Theta isn't dependent upon radius, because 1 revolution is 2 pi radians. But the distance that it travels is dependent upon that radius. Okay? That's the bigger key. So, if you go back, and this is where this all kind of comes together, if this is my wheel line, what's that line going to look like for that 100 gram max?
Real small.
Mad Max.
It's going to have a very small slope
Why?
because it's got a really small radius.
Yeah. So if I go through 2 pi radians with that 100 gram mass, guess what? It's going to be a pretty shallow line because of the fact that the slope represents radius. So in 1 revolution here, I'm only going to travel, you know, maybe 0.1 meters, whatever it is. Whereas with that bicycle wheel, I'm going to travel 1.57. Now, what about the Earth? So here you are with the Earth. And we got Big Al here, right? So Big Al is coming around like this, okay? And he's going to make 1 revolution. How long does that take?
24 hours.
24 hours, right? So that's going to be a big monster radius, right? 6.3713 times 10 to the 6 meters. So if you do the same thing for the Earth, you're going to make 1 revolution. You're going to go through 2 pi radians, even on the Earth. But what's going to happen to that line? It's going to be really, 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 really steep because the Earth has a really, really, really big radius. Okay? So this is where you have to keep in mind what's a factor and what's not a factor. Okay? That relationship between revolutions and radians is not dependent upon a radius. But a graph like this is dependent upon the radius. So that's what you've got to be able to think through. Now, let's say, and we're going to do the same thing again. We're going to have it here, right? But now we're going to keep track of how long it takes, right? So we're going to start here. We're going to go 1,001, 1,002, okay? So that took about 2 seconds for it to go. Once you know time, then what can you start to look at?
Velocity.
Velocity. Then you can start to look at how fast it's going. Now, for the sake of argument, for the sake of argument, we're going to pretend that the crossover equations don't exist. And I'm going to tell you that tire is here, okay? And we're going to make 1 rotation, and that's going to take 2 seconds. So here's what I want to know. I want to know how fast that wheel is moving across that table. So at the end of the day, I want to calculate a linear velocity. I want to know how fast that wheel is moving. So what's the simplest thing that I can measure to get that velocity? What are the 2 things that are simple to measure?
Distance and time.
Distance and
Time.
time. So I know, now do I know how far it goes? It made 1 revolution. Do I know how far it goes?
Yeah.
It's going to travel the circumference, which is,
2 pi out.
so I still got that same radius, right? Radius is 1.57 meters. So I know that, excuse me, that's 0.25. The radius. So I know when it travels 1 revolution, this thing is going to travel 1.57 meters. So if I take 1.57 meters and divide that by 2 seconds, so somebody hit 1.57 divided by 2 is 0.7 something.
0.785.
So I'll call it 0.79. Okay? So now, here's what that tells me, and this is important. You've got to understand this. This number tells me 2 things. It tells me how fast the center of the wheel is moving going down the road. Okay, that's one thing that it tells me. It also tells me that if you were walking along the outside of the wheel and you wanted to keep up with a point, that would also tell me how fast you have to walk. Okay? So that's what that's going to tell you. Or the other thing you can view it is that imagine that you've got a little speed gun, okay, radar gun, and you shot that radar gun, and that would tell you how fast the outside tire is moving. That's the other way that you can view it. So anytime you have meters per second, okay, anytime you have meters per second, that's going to be referred to as like the tangential or linear velocity. It's how fast it's moving or how fast a point is moving on the circle. Now, you're like, okay, well that's cool, Burkamp, but what about the crossover equation? Okay, let's talk about that. So, pretend that this doesn't exist, it's gone, okay? We'll move on. So, I want to find omega, which is going to be theta divided by time. So, when that thing rolled, how many revolutions did it move through? Tori, how many revolutions did it move through? Don't make this difficult. How many? One. And one revolution is how many radians? 2 pi. So this is going to be 2 pi radians. Now, how long did that take? 2 seconds. Right? So that's going to take 2 seconds. So, divide that out, right? So basically, you get pi radians per second. Okay, so we'll call that 3.14. So what that means is that you're moving at 3.14 radians per second. That's your value for omega. Now, here's what I want you to look at. Okay, this is one of the most important things that you all are going to screw up. Have I talked about radius yet? No. So here's what's important. Is that every point on that wheel, okay, is moving at 3.14 radians per second in terms of an angular velocity. Where you are on the wheel doesn't matter. Radius is not a factor. Okay? Just like if I double the mass of a satellite, what does that do to the period of the satellite?
Nothing.
Nothing. Why?
Because mass doesn't matter.
It's not there. Okay? If I'm talking radians per second, okay, the radius of the tire is not there. This could be an electron moving around the nucleus of an atom, whatever. Okay? Doesn't matter. Does not matter. So here's the deal. But now I know that radius is 0.25. So now I can go, oh, V equals R omega. Now I can use this, because now I know what my omega is. So now I can go, oh, okay, I can do this. That's 0.25 meters times 3.14 radians per second. So somebody take 0.25 times 3.14. You should get
0.75.
0.79 meters per second. This is the exact same thing. Okay? Now, here's what's important. You'll notice that radius is a factor in this calculation. So what that means is this. If I get this wheel spinning, and Bree's got a little radar gun, okay? Where on the wheel would Bree record the smallest speed? Near the center, or toward the outside, or would it be the same? Keeping in mind her gun is measuring in meters per second.
Near the center.
The center, why? And it's going to travel in the same amount of time. Okay? So she would record the smallest speed in terms of meters per second closest to the center. She'd record the highest speed on the outside. Right? So, if you're talking, and this is what you have to keep straight in terms of terminology, angular velocity is always going to be in radians per second. Linear or tangential velocity is going to be in meters per second. Okay? You have to keep the two straight because they are vastly different things. Now, believe it or not, every time that you have driven a car, you have used that equation. And you're going, Burkamp, I've never seen that equation before in my life. You have, you just don't know. So let me give you a quick lesson in auto mechanics. So, here's the engine of your car, okay? And it's going to transmit power out to your wheels, okay? Right? So, somewhere in here, there is a sensor that keeps track of how some part is moving. Sometimes, in the old cars, it used to be like a mechanical system. Now it's an electronic sensor. But something somewhere is keeping track of how fast something is spinning. Okay? Then what it does is that it translates it into V equals R omega. Because when you're looking at your speedometer, what is your speedometer giving you? The rate at which your car is moving or the rate at which your tires are moving?
Get your cards moving.
Yeah, the entire car is moving. So what happens is that when your car came out of the factory, this was calibrated to a certain size tire. So if you open up your driver's side door and look on the frame, you're going to find information about tires. And it's going to say, this is the size of tire that you should use. Because so what it basically does is says, okay, I've got this internal part that it's spinning at a certain rate. Here's the radius of your tires, and based upon that calculation, that means the car should be going 20 miles per hour. And your speedometer is going to indicate that it's going 20 miles per hour. Now, let's say that you're in the rebel stage of your life, okay, and you can't like abide by the speed limit. Like you have to break the speed limit. I'm just a rebel. I'm raging against the man. Okay, let me know how that works. So you've gotten speeding ticket after speeding ticket. Mom and dad are ready to kill you. Your insurance company is ready to drop you, but you're not smart enough to realize, man, maybe I should kind of follow the speed limit. And more importantly, you hang out with a bunch of idiot groupies that you want to impress that think that you're breaking the law, okay? Hypothetically. So you still want to appear, like you still want to think that that you're breaking the law. Like you want to think people are driving 40 when actually you're not. So here's the question. How can you appear to still be driving 40 miles per hour, but yet be going slower than that? Would you want to put on bigger tires or smaller tires?
Smaller.
Smaller tires. Why?
Because it's going to have a lower top speed. Yeah. Well,
Why?
because it has a lower rate, smaller radius.
So for every revolution, you won't go as far, right? So imagine that you take your car and you put on like small little mower tires, right? Okay? Put on small little motor tires. So you can be cool and go, oh, look at me, I'm breaking the law, I'm driving 40 into 25. And in reality, you're probably driving, maybe depending upon the size of the tires, maybe 30, 25 miles an hour, something like that. So you can still appear cool, okay, to your little groupies in the back seat who probably aren't paying attention anyway. They're probably staring down at their phones. But in case they do look, you can go, look at me, I'm cool. Now, the other extreme, and this notoriously happens to guys, okay? This notoriously happens to guys. Not always, but notoriously. So notoriously, guys go out, they buy four-wheel drive trucks, and what's the first thing that they do with it?
Put huge tires on
They
it.
lift it and they put on huge tires, right? Okay? So then they put on big, oversized tires, right?
Yep. Yes, sir.
So now,
Then you're going fast.
when you think your speedometer says you're going 40, you're actually going,
60.
well, probably not 60, but certainly going faster like that, right? So then the police officer pulls you over, whoop, whoop, okay? But we go, officer, I was driving the speed limit. And the officer goes, where'd you take physics at? Mays High School. Did Miss Mercap never teach you V equals R omega and the influence of the diameter of your tires and how that affects your linear speed? And if you say no, okay, I will personally go testify in court against you, okay? I will roll you under the bus.
Have you ever had to do this yet?
Huh?
Have you had to do
No,
this yet?
but it's a good threat. So, because here's the deal. If you're going to put on oversized tires and you think you're driving the speed limit, you're not, okay? So, you're going to be going faster than what you think. So, just keep that in mind if you get the urge. I'm sure Marion's going to go buy like a little Toyota four-wheel drive pickup, put big monster tires on it, Yeah.
Is the big, with the wheel, it affects the slower acceleration and the smaller wheel.
Marrying a big southern people.
That gets...
Yeah, I'll get on this.
Eli,
Assuming
you don't know what
Yeah.
awesome is.
Okay.
Mountains of
All
dead
right,
people.
now we have one
Nothing
thing. Now,
awesome.
here's the other thing. And just like this, you can have like A equals R alpha. So let's say, for example, that you're in your car, right? So what's the purpose of the gas pedal in terms of linear acceleration? Make it go faster, right?
Yeah.
So if on your car, if you can figure out your linear acceleration, okay, you're going from 0 to 20 meters per second in a certain amount of time, and you know the radius of the tires, then you can calculate the angular acceleration of your tires. So every equation that you've ever worked with it's the exact same idea. We're just using different variables. Okay, so don't flip out of this. All right. So we have one thing left to do, and this is another thing that you've dealt with probably even since before you could walk, even just when you were toddling. So here I've got this balance beam. Catch that? Okay. Now, I've pretty much got it balanced.
Concentration.
Okay? So here's the question. How can a little weight out here balance out a big weight on that side?
More torque.
Balance point.
More torque.
Yeah. What's that called?
Torque.
It starts with an E, doesn't it?
Torque? No.
It's torque.
I don't think it is.
It is.
Oh,
It's
wow.
torque. Okay? So torque, let me give you a hint. Torque involves two things. So based upon this demonstration, what are the two things that affect torque?
Distance.
Distance and
No.
not,
Weight.
but weight's a measure of force. So there's two things that affect torque. There's how much force you apply and
Distance.
where you apply it, right? So based upon this, do you think the two torques are the same?
Yeah.
Yeah.
Yeah, because if this was quite a bit more, what would happen? Yeah, because if I take this and I move this farther out, we go doink, right? If I move it further in, I go doink that way, right? So to make this thing balance, I can find that one point. Almost. There we go. Where the two balance out. So when you talk about torque, torque is a product of two things. It's force and radius. So let's look at this force over here. Okay? So on this side of the balance beam, I've got a 100 gram mass that is about 25 centimeters out. So I need force and radius. So what am I going to do? Have to do with the 100 grams? Convert it into newtons, right? Well, but I convert it into kilograms first, right? Because fundamentally, what's creating the force? Gravity. That 100 gram mass is interacting with the gravitational field of the Earth, right? So that force would be 0.1 kilograms times g times the radius of 0.25 meters. So somebody take 0.98 times 0.25. It should be around 0.25.
0.25.
Is it 0.25?
Yeah.
Okay. Now, what units do I have? Don't make this difficult.
Newton.
Newton meters, right? Because this gets me newtons, which is force, and then that distance, which is meters. So I get Newton meters. Okay, nice. Now, in the English system, we actually use like foot pounds. It's the same idea. So if you ever watch like truck commercials for like Dodge, Chevy, whatever, they'll go, oh, we have the largest carrying capacity and the most foot pounds of torque. Yeah, so that's what that's measured in. So in the English system, instead of Newton meters, it's foot pounds. Okay, that's where it comes from.
Because that's it's force.
Now, so how can this one over here balance this out?
Because it's a larger mass, even though it has a smaller radius.
So that's got a smaller radius, but a
Larger mass, larger force.
larger force. So are the two torques the same?
Yes.
Yeah. So basically what I've got going, when I look at this torque, I've either got on that side, on your side, I've got a big force and a small radius. Over here I've got a larger radius. Okay? So you're going to balance out. Now, here's the other situation that you've used torque. Okay? So give that a spin. So there's two, when I go to open up this door, there's two places that I can push. I can either push out here on the edge, or I can push right here by the hinges. Now, in which situation is it going to take more torque to open the door? Hinge.
It's the same.
Hold on. Outside, inside, or it's the same amount of torque?
It's the same.
Same amount of torque, right? Okay? Torque's going to be the same. But if I push really, really close to the hinges, what's going to happen?
You need a large force.
More force. Why?
Smaller radius.
Small radius. So I can open up the door right here and push, but it's really, really tough to do. Okay? Now, out here,
Just bust out that shirt.
that's why I wore the vest, just in case. What? That's not funny. It's a true story. I knew I was going to have to do this demonstration because that happened. It was just awkward. Okay? Kind of had this Hulk thing going. Oh. So, all right. So, no matter where I push, guess what? It's the same amount of torque. But out here makes it less force, so therefore it's easier to open up the door. So that's what I said. Even since you guys were little toddlers, right? And you were crawling around on the floor, you were getting into cabinets, right? Okay? Why? Toddlers figure out torque pretty easy. Because where do they go to pull? Easy spot. So if you'll notice, with hinges, hinges are always here, right? Could you put the hinges here?
Yeah.
Yeah, it isn't like, it isn't like a building code that says, oh, you've got to have the handles in the middle, okay? You could put the handles here. It wouldn't make, they would still open. But, yeah, especially, so if you have little kids and you're worried about them getting in, put your handles out here. Okay? So, torque's going to be the same. It's just how much force that you have to apply. Okay, so stop that. Let me hand out these things.
Dang it, I'm only 8 minutes short. 8 more minutes.
Okay, now, let's talk about problem number one. So I want to make sure everybody starts off correctly. So, on problem number one, you're going to look at the fact that you're trying to find omega for a clock, all right? So we're going to talk about the hour hand, the minute hand, and the second hand. And I want to find omega. So since they're spinning at a constant rate, I can use theta over time, all right? So let's talk about the hour hand, which is right now kind of pointing towards the 1, okay? So here's my question. That smaller hand is pointing towards the 1. How long is it going to take for it to get back to that point?
Oh. Yeah, 12 hours.
12 hours?
Yeah.
Yeah.
Yep. Or 24. No.
Or 24?
Or
Definitely 12.
They're keep on 38.
Wait, we're sure it's not something.
Everybody cool with 12 hours? Why?
because it's going to be
One revolution.
Yes.
counter.
So the next time it points back there will be about 10 till 1 in the morning,
Yes.
right? So your hour hand is going to go through 1 revolution, which is going to be 2 pi radians. But that's going to take
Matt, no.
12 hours. So what are you going to do with the hours?
2 minutes, seconds.
Convert them into seconds.
Seconds.
So is this going to be a big number or a small number in terms of
Big.
omega?
It's gonna be real
It's
small.
going to be a small number. Okay? Your hour hand is not moving through very many radians per second. Okay? It's going to be a very, 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 very small number. Now, let's talk the minute hand. So the minute hand right now is about somewhere between 10 and 11. Right?
Wait, do we need to put a calculator in degree? I mean,
No.
radian mode?
No. All you're just taking 2 pi and dividing it by the number of seconds.
Oh, that's right.
You don't have to worry about that if you're using trig functions.
Okay.
Okay? So here's the question. How long is it take for the minute hand to go back around?
60 minutes.
That's going to take 60 minutes. So your minute hand, you're going to take 2 pi radians, and you're going to divide that by 60 minutes. Now, what about the second hand?
60 seconds.
That's going to take 60 seconds. So of the three, which one is going to have the highest angular velocity?
Second.
Second hand, because that takes the smallest amount of time to make one revolution. Now, let's step back for a second on problem number 1. Did I give you the radius of the second hand or anything like that?
No.
Why?
Because it doesn't matter.
It doesn't matter. So it doesn't make any difference if it's this watch, the clock up there, Big Ben in downtown London. It doesn't matter. Okay? They're all going to travel the same number of radians per second. Okay? They're all going to have the same number of radians per second. Now, however, if you look down on question number 2, I say, what's the linear velocity? Linear velocity, that's when we use that V equals R omega. So your linear velocity is a measure of, if you want to think about it, like imagine that you're shrunk and you're inside your watch. Your linear velocity is telling you how fast you have to walk to keep up with that point. Is your linear velocity dependent upon radius?
Yeah.
Yes, that's why I had to give you the radius so you could do that calculation. Okay? Now, when you get down to number 9, okay, you got Bubba and Betty Joe. So here's what's happening on number 9. You have a teeter-totter, the fulcrum is in the middle. You got Bubba on one side and you got Betty Joe on the other. They want to balance out. So what you're trying to figure out is how far they have to be from the center. Okay? Make the two torques equal, make the torque of Bubba equal the torque of Betty Joe. Now, number 10 is more difficult. Okay, so let me get you started on problem number 10. So here's the problem with number 10. You've got a board that's 1.75 meters long. Okay? That's the length of the board. You've got George on one end and you've got Joe on the other. Here's the deal. You want to figure out where to put the fulcrum so that it's balanced. Now, look at your numbers. George has a mass of 56 kilograms. Joe has a mass of 43 kilograms. Okay? So this is 56, this is 43. So is the fulcrum going to be closer to Joe or closer to George?
Closer to George.
Closer to George. Okay? So I'm going to put that fulcrum somewhere over here. I don't know where. Now, what are the two things that are going to contribute to the torque of George? Force and?
Let's say horse.
Force. Okay. So, does the torque of George have to equal the torque of Joe? Yeah, otherwise it won't balance, right? So this is going to be the force of George, but you don't know where to put the fulcrum. So what can you let the distance to George be?
A variable.
How about X?
How about
No.
Decision.
How about that?
How about it?
How about that?
Yeah.
How about that?
Now, that's going to equal the force of Joe. Now, this is like the Lagrange problem that you work with the moon, although not as complicated. So with this one, if this distance is x, and the entire length is 1.75 meters, how much is left over?
1.75 minus that.
1.75 minus x. And then it turns into an algebra problem. So you've got the mass of Joe, you know what G is. You got the mass of George, you know what G is. Put all your x terms on one side, put all the other ones on the other. Now, when you get to on the back side, okay? Like for example, if you get like a number 17, spinning wheel is an angular velocity 50 radians per second, it's accelerated 5 radians per second squared. What's the angular velocity at the end of this time? Now, let's just think this through. Is the wheel already spinning?
Yes.
Yeah, it's already moving, right? Is it going to speed up or slow down? How do you know it's going to speed up?
Because the acceleration is positive.
And the velocity is positive, right? So it's the same idea. So if you look on problem number 17, you have an initial velocity, you have an acceleration, and you know time. What's the only thing that you don't know? Final velocity. Now, if you don't know how to work that problem, and you're flipping out going, God, I don't get this whole radian thing, Burkham, this is horrible. Change the problem into meters per second. Go, oh, it's moving at 50 meters per second, it's accelerated at 5 meters per second squared for 12 seconds. What would my linear velocity be? So if you can think it through that way, then go back and say, oh, it's the exact same mathematical relationship. Okay? Like on this one, draw a velocity time graph. Oh, okay. I'm at 50. How does that 5 radians per second squared play into that omega time graph? What's that 5 radians per second squared represent? Slope. I'm starting at 50, I'm going to be going faster. Okay? So literally, if you get in those problems and you don't know what to do, think it through in terms of linear process, and then switch back over to an angular process.
2 different languages.
Yep. Okay, I'm done. You're on your own. You got to hit an hour?
Yeah, by like 50 seconds.